Let's introduce some terminology to explain how concatenating data frames in series works. Let's consider stacking two-dimensional arrays first. We'll create three matrices by creating a range of consecutive integers using range, transforming a one-dimensional array into a rectangular shape with the reshape method, and adding different constants to make them easy to distinguish. That is, we make a 2x4 matrix A, a 2x3 matrix B, and a 3x4 matrix C. We can stack the 2x4 matrix A and the 2x3 matrix B horizontally using np.hstack. The input is a list of NumPy arrays. Equivalently, we can use np.concatenate with the same sequence and axis equals 1 to append columns horizontally. In both cases, both A and B must have the same number of rows, although the number of columns can differ. We can also stack the 2x4 matrix A and the 3x4 matrix C vertically using np.vstack or np.concatenate with axis equals 0. Again, it's important here that both matrices have 4 columns. The argument axis equals 0 is actually the default and optional. A value error exception is raised when the arrays have different sizes along the concatenation axis. For instance, trying to stack arrays A and B horizontally or A and C vertically causes problems. Let's return to the population and unemployment data indexed by zip code. When loaded, population has 4 rows and 1 column, while unemployment has 4 rows and 2 columns. Again, the indices of these two data frames differ in all but one row with zip code 2860. Remember, Pandas was developed after NumPy. Let's pretend we've received these data frames as NumPy arrays by converting them to arrays with the NumPy np.array constructor. When we do this, the index information is lost. There are simply two NumPy arrays of dimension 4x1 and 4x2. We could apply np.concatenate or np.hstack to these two arrays to yield a new array of dimension 4x3. But this result is meaningless. The rows are glued together independent of the original meanings. We would have to store the zip codes in other lists or arrays to align rows properly. It turns out that appending labeled tables in this way corresponds to what is called a database join. Joining tables involves meaningfully gluing indexed rows together. We'll look at more types of joins later, but let's focus on outer and inner joins now. An outer join preserves the indices in the original tables, filling null values for missing rows. An outer joined table has all the indices of the original tables without repetition, like a set union. Conversely, an inner join has only index labels common to both tables, like a set intersection. Let's make this concrete with the population and unemployment data frames. We call concat along axis equals 1 and explicitly specify join equals inner for an inner join. This means only the row label present in both data frame indexes, 2860 in this case, is preserved in the joined data frame. The column values in this single row are filled in from the corresponding columns from the population and unemployment data frames, respectively. When we specify join equals outer when concatenating along axis equals 1, we get an outer join. This is the behavior of concat we originally observed because, if unspecified, the join parameter defaults to outer. All row indices from the original two indexes exist in the joined data frame index. When a row occurs in one data frame but not in the other, the missing column entries are filled with null values. Notice we could also do an inner join along axis equals 0 instead. The resulting data frame is empty because no column index label occurs in both population and unemployment. Try your hand now at computing inner and outer joins when concatenating data frames in the exercises. We can stack data frames vertically using append, and we can stack data frames vertically or horizontally using concat. Concat is also able to align data frames cleverly with respect to their indexes. However, very often we need to combine data frames either along multiple columns or along columns other than the index. This is the world of merging Pandas data frames. To be clear, merge extends concat with the ability to align rows using multiple columns. To demonstrate, let's load a small data frame population with 5 rows and 2 columns, zip code and 2010 census population. This data comes from the state of Pennsylvania from the 2010 census. The index is a range of integers from 0 to 4. The longer data frame cities has 15 rows and 3 columns, zip code, city, and state. The state column is uniformly the string PA for Pennsylvania, and again, the default index is an integer range. What we want to do is merge these two data frames into one, linking city names and populations to a given zip code. That is, we want to combine the data frames and do so aligning the zip code column. We do this with the pd.merge function. This computes a merge on all columns that occur in both data frames. In this case, this is only the zip code column. What this means is that for any row in which the zip code entry in cities matches a row in population, a new row is made in the merged data frame. That new row contains the row from population with the other columns from the corresponding row in cities appended. Thus, the merged data frame looks like population with other columns from cities on the right. This is, by default, an inner join, as we saw previously. It is an inner join because it glues together only rows that match in the joining column of both data frames. Let's try again using the top 5 bronze and gold medal-winning countries from the Summer Olympics. Both data frames have 3 columns, the country code NOC, the country name, and the total number of medals won. By default, merge uses all columns common to both data frames to merge. That is, the rows of the merged data frame consist of all rows where the NOC, country, and totals columns are identical in both data frames bronze and gold. Thus, this merge yields an empty data frame because the total columns never match. Instead, we can choose a particular column to merge on, NOC in this case. This means matches are sought only in the NOC column. Remaining columns are appended to the right. The column labels are modified with the suffixes _x and _y to indicate their origin, x for the first argument to merge and y for the second, bronze and gold in this case. Observe the columns country _x and country _y are identical. To eliminate the redundant country column, use on equals NOC, country to merge on both of those columns. This is where merging extends concatenation in allowing matching on multiple columns. The result has only one column for country. The total columns still have suffixes _x and _y to indicate their origin. We can tailor column labels with the argument suffixes. This replaces the suffixes _x and _y with whatever custom names we choose. Thus, we now have a much tidier table without redundant columns and with the totals labeled appropriately. Merging works well when the column labels match. Let's figure out what to do when they don't. We load a data frame counties that we want to merge with our data frame cities from before. The column city name in counties has a few similar entries to the column city from cities, even though their column labels differ. As the labels differ, we have to declare which columns to merge on. Specifically, we look for matches in city name from the left data frame counties and city from the right data frame cities. Notice both columns are retained in the merged data frame. Switching the order of the left and right data frames in the call to merge yields a permuted data frame. That is, the order of the rows and columns are different, but the content is the same. This is a lot to absorb for now. Try merging some data frames using column values in the exercises. Pandas has to search through data frame rows for matches when computing joins and merges, so it's useful to have different kinds of joins to mitigate costs. Let's explore joining more closely. To start, load the bronze and gold Olympic medal data again. The function merge does an inner join by default. That is, it extracts the rows that match in the joining columns from both data frames and it glues them together in the joined data frame. We can specify the keyword argument how equals inner, but this is in fact the default behavior for merge. Alternatively, using how equals left keeps all rows of the left data frame in the merged data frame. For rows in the left data frame with matches in the joining columns of the right data frame, the non-joining columns of the right data frame are appended to the left data frame. For rows in the left data frame with no matches in the joining columns of the right data frame, the non-joining columns are filled with null values. That's really quite a mouthful. As an example, when doing a left join with bronze on the left and gold on the right, the row for France is retained and a null value is inserted into the total gold column because gold has no France row. Conversely, using how equals right does a right join doing the same thing with the roles of left and right interchanged. Thus, here we retain all 5 rows from the gold data frame. This time, Italy has a Nan entry in the total bronze column because bronze has no Italy row. Finally, the union of all rows from the left and right data frames can be preserved with an outer join. With the argument how equals outer, we can clearly see that France was not in the top 5 gold medal winning countries and Italy was not in the top 5 bronze medal winning countries. To understand a bit better how joining works, let's examine the census dataset again. We load 2 5-row data frames, population and unemployment, indexed by zip code. Remember, the only common row label is 2860. Pandas data frames have a join method built in. Calling population.joinUnemployment computes a left join using the index by default. Only the row 2860 is complete. The remaining rows are preserved from population with the unemployment and participants columns filled with nans. The row order also matches that of the left data frame in this case. The join method can also do a right join using how equals right. In this case, the 2860 row is preserved again, but the other rows are extracted from the right unemployment data frame with the 2010 census population values set to Nan. Notice the row ordering matches that in unemployment this time. The join method also supports inner and outer joins on the indexes. Here is the inner join returning a single row exactly as computed using pd.merge. And here is the corresponding outer join. As before, all rows have some null entries except one. Notice the outer join sorts the combined index. We've looked at a lot of equivalent pandas tools for joining. Which one should you use? Occam's razor is a good principle here. Use the simplest tool that works. If you only need to stack 2 series or data frames vertically, the append method is sufficient. If you need more flexible stacking, or an inner or an outer join on the indexes, the concat function gets you further. The join method also joins on indexes, but gives more flexibility for left and right joins. Finally, the merge function is the power tool for joining when you need to join on several columns. That's a great deal of material to absorb. Try your hand now at joining in the exercises to make sure it all makes sense.